Hello everyone, a very good afternoon to all of you present over here. It is my immense pleasure to welcome you all on behalf of Department of Computer Applications of BP Poddar Institute of Management and Technology in the 5-day workshop on machine learning in data science. I am very glad to say that more than 600 I, on behalf of the Department of Computer Applications, would like to express my sincere gratitude to our principal madam, Professor Dr. Sutopa Mukherjee, Emeritus Professor and former Dean Academics, Professor Dr. B.N. Chatterjee, Registrar Sir, Dr. Subhashish Pradhan, convener of this event, and Assistant Professor of Department of Computer Applications, Ms. Inaduti Dutt, and all the committee members of this event for their constant support and enormous effort towards organizing this event. Without taking much more time, I would like to invite our principal madam, Professor Dr. Sutopa Mukherjee, to inaugurate this workshop and also welcome our guest speaker and participants in this 5-day workshop on machine learning in data science. Please, ma'am.
Am I audible?
Yes, ma'am.
Yes.
Respected Emeritus Professor B.N. Chatterjee, today's speaker Professor Amlan Chakraborty, other esteemed speakers, members of BPPIMT family, and all the external participants. Warm good afternoon to all of you. I hope all of you are well during this pandemic period. At first, as head of the institute, I welcome you all to this 5 days workshop on machine learning in data science, organized by the Department of Computer Applications of BP Poddar Institute of Management and Technology. The workshop will be held during 11th to 15th August 2020, and during these 5 days, we will get the opportunity to hear from eminent speakers from various domains. From academia, we will have Professor Amlan Chakraborty, Professor and Director of A.K. Choudhury School of Information Technology, University of Calcutta, Professor Shomarjit Bora, Professor and Head of IT Council, SMIT, and Dr. Surabhi Dasgupta, Associate Professor of St. Xavier's College. From industry, we will have Mr. Aurav Bhatt from IBM, Mr. Abhijit Mollik and Mr. Brotin Dash from Sofan Based Technologies. In addition, also there will be 2 alumni members of this institute of 2017 pass out batch. They are much younger. Mr. Rajan Brahma, product engineer of Ovens, and Mrs. Atoshi Nath, software engineer, Mobile Wala Information Solutions Private Limited. I must say that the selection of topic is very relevant, and in my opinion, this is the need of the hour. So I'm sure this workshop will be beneficial for all of you. My sincere gratitude to all the speakers for accepting our invitation, and I appreciate this initiative of organizing this workshop for utilizing this pandemic period in a positive way. I'm sure the participants will be able to enrich their knowledge from the sessions of the esteemed speakers. Thanks to the convener, the coordinators, faculty and student coordinators, and all the members for this initiative. And special thanks to all the participants from West Bengal and all other states of the country for joining us. And I wish the program a grand success. Thank you.
Thank you, ma'am, for your valuable speech. Now I introduce our speaker, Professor Amlan Chakraborty, sir. Professor Amlan Chakraborty is a full professor in the A.K. Choudhury School of Information Technology at the University of Calcutta. He is also the Dean Faculty of Engineering and Technology of his university. He is an MTech from University of Calcutta and did his doctoral research at the Statistical Institute, Kolkata. He was a postdoctoral fellow of the School of Engineering, Princeton University, USA during 2011 and 2012. He is the recipient of prestigious DST Boy Scout Fellowship Award in Engineering Science 2011, Indian National Science Academy Visiting Faculty Fellowship 2014, JSPS Invitation Research Award 2016, Erasmus Mundus Leaders Award from EU 2017, and Hamid Visiting Professorship from University of Cambridge 2018, and Shiksha Ratna Award by Department of Higher Education, Government of West Bengal 2018. He has also served in various capacities in various higher education organizations, both at national and international level. He has been associated with reputed international and national institute of repute as a visiting professor, to name a few: University of Sunny Buffalo, USA, GSI Helmholtz in Research Laboratory, Germany, University of Berlin, Germany, CERN Geneva, Kushu Institute of Technology, Japan, Lincoln University College, Malaysia, University of Oradea, Romania, University of Cambridge, and City University, London, UK, etc. He has received multiple project grants in the areas of security in cyber physical systems, embedded system design, VLSI design, quantum computing, and computer vision, data science from various national and international agencies like DST, DRDO, MIETY, UGCTAE, Ministry of Social Environment, TCS, etc. Till date, he has graduated many
सर
PhD
आधा
students.
ज्ञान सब यूट्यूब पे पाया
He has published around 125 research papers in referred journals and conferences. He is a senior member of IEEE and ACM, distinguished speaker of ACM, secretary of IEEE CEDA India chapter, and life member of CSI India. Now, I would like to welcome our Omlan Chakraborty sir to take the session.
Yeah, thank you, Professor Orijit, and thanks to the principal madam for this great inaugural program, and I thank the Department of Computer Application for inviting me in this webinar to present to you all, and I especially thank Inaduti for keeping communication with me and for informing me all the things what for this particular webinar. So, my talk of today's talk will be even machine learning, which is obviously a very well discussed topic, and also a lot of students, and primarily I'm giving this lecture for the students of this institute. And this is obviously a particular topic where the students get a lot of interest in the present days, because obviously it has a lot of scope in terms of both professional activities in terms industry and jobs, as well as they have immense scope in the research area also. So without wasting much time, I will start my presentation. And this presentation I have kept for around 1 hour 30 minutes, and after that I will be fine to take questions, and if time permits I can also show you some of the because in this pandemic scenario the most vital question is that, provided we learn a particular topic, how we can develop the programs for this particular domain. So I will also give you a little bit glimpse of the Google Colab platform, which you can use through your that means if you have internet, you can connect to Google Colab, and you can develop very useful programs which can help you to learn this machine learning domain. So so I'm start presenting my talk. Okay. So I hope my slide is visible to all of you, right?
Yes, sir. It is visible.
Okay. Okay, great. So the talk is the title of the talk is Machine Learning and Exploratory Tool, and we will surely try to understand that how machine learning explores the data, right? And that's the fascinating part of machine learning. And obviously, I will try to discuss that what are the insights of the machine learning tool, so that you can develop the concepts or about the various techniques of machine learning, and you can use those concepts in the developing of the programming models or the programming executions. Uh, so again, I thank the Department of Computer Applications for organizing this webinar. So I start with some introductory concepts where I will give you the very basics of the machine learning, so that we can just try to understand the impact of this in the present computing domain, and slowly I will progress onto the techniques what are involved in this fascinating domain of computer science. So, if we see machine learning, the machine learning has that means it's not that machine learning only started for the last 10 years. Though in academia and in our activities and research, we started working with machine learning maybe for the last 15 years. Okay, people started working from AI. There was a slow migration to machine learning. But the concept of machine learning, which was coined by Arthur Samuels, who is the father of machine learning, uh, the concept was developed in 1959. It's a pretty long time, right? We have around 70 years. And the concept was developed. And what he told that there will be some sort of machines or computers, right, which will be able to generate outcome, or generate very effective outcome without being explicitly programmed. So normally, when we look into the computer programs, right, the way we start is that we try to look into the problem, right, and based on the problem, we try to find out that what are the possible solution paths we can frame for the problem, based on the different types of algorithmic approaches we know, right? It can be a searching problem, it can be a sorting problem, it can be a graph analysis problem, it can be a tree search problem, something like that. I'm just giving some very simple way. So provided we try to map this problem to a specific class of algorithm, right? And then we try to make the algorithm very specific to the particular problem by including a lot of constraints and the functions which are required for the particular domain. And then we try to convert the algorithm to a program, and then we try to put the program in the machine, right? And the machine executes my algorithm or my program. So this type of development is called explicitly programmed development, which means that the program is not evolved, but the program is rather developed, right? And this type of program has limitations, right? Limitations in the sense that, okay, that means if I have done a program which is that if I have done a program which works in my indoor environment, right? It's a computer vision program which works in an indoor environment, right? The program fails in the outdoor environment because the way the program has developed, the program doesn't it cannot execute itself when the scenario gets changed, or it cannot give a good outcome when the scenario gets changed, because the program is not adaptive program. Whereas Arthur Samuels told, that means said that there will be a particular way of computer programming, which will be not like this type of static programming or explicitly programming, but the program will evolve and will try to modify itself, right, with changing scenario, right? And that's what is an evolving programming scenario, which is not explicitly programmed, and that's where machine learning leads all of us, right? And that was exactly predicted by Arthur Samuels. This was another way of trying to understand what a machine learning is, as coined by Tom Michels, in 1997, where he told that machine learning is a type of program which improves its performance. Okay, that means any any job we do in our computer, okay, using our computer can be coined or can be named as a task, right? Say we are trying to find an object in a okay, in a given image, right? So the task is object detection or object recognition. So this is a task, right? And this task has a performance, right? Performance means that out of maybe 10 images, okay, maybe 5 images the objects were detected correctly, in 5 images not. So the performance is 50% of this particular my computer program. But can we improve the performance? Yeah. So machine learning algorithms, a machine learning based program can improve its performance, and the improve its performance is through experience, and that experience is nothing but the term learning. So the term learning, which is associated in the word machine learning, which means a machine and learning. So the learning is something by learning means the gather of, that means aggregation of knowledge to experience. So how the experience comes? The experience comes by the interaction of the machine with more amount of data or more number of scenarios. So if we try to expose the machine or my program or my model to a larger variety of data, right? Which means that larger variety of scenarios, right? My machine will be more powerful, right? And because the machine has got more experience now, as it has got more experience, it becomes powerful and its performance gets enhanced, right? And that is the other way of looking into this machine learning algorithms, right? And that we will see that what this particular learning means. But the most fundamental assumption of machine learning is that we require data. So the way we try to develop the programs here is that it's not actually called a program, but it's actually called a model. So the model is developed through a learning procedure, right? And the learning procedure is done by means of the data, provided we have made the model learn well, okay, and very exhaustive learning has been done for the model. Then the model is well suited to work with the data which is still unknown. So what we do, we try to train the data, train the model with some known data which has known outcomes, right? And we try to develop the model with certain accuracy. The accuracy should be pretty high, and provided we do that, then this model will be fine to work for the data which is coming. For example, for a very simple way, I can tell that if I want to make a model which will predict the agricultural yield of my country, right? So how I can go forward? So I can go forward is that I know that what are the parameters which my agricultural yield depends, right? It depends on the rainfall, right? It depends on the amount of the harvest, the amount of the land which is being used in the harvest, right? It depends on some sort of soil conditions of those lands, right? And also it depends on the amount of physical labor the farmers give into this particular job, right? So this is that I am not agriculturist in that sense, but I'm just trying to give you a toy example. So provided I get the data for the last 10 years, right? That means I build a model that maybe this is the agricultural yield. Maybe I can make a model very simple. This is the agricultural yield. If this is the average temperature variation in a year and rainfall variation in a year. Okay, that means I get the data of temperature variation and rain variation of the last 10 years, and I get the data of the agricultural yield of the last 10 years, right? And try to find the way that means, and try to find a correlate, that means a particular model which actually accepts that means takes these values, the temperature and the rainfall amount, and try to predict the yield. If I can generate the model, now this model I can use for the next year, right? For the next year, I can that means I can just try to find what is the prediction of my rainfall and average temperature, and from that I can try to predict the amount of crop which will be yielded in a year. So these are the ways I first of all build a model with my existing data, and then I use the model to predict or classify the unknown data, and that's what is the fundamental of machine learning. Now, as I told that how a task can that means how the performance of my model or how the performance of executing a task increases. That's also a simple example which is given here, okay, in the example of my slide, which tells that suppose I try to predict the traffic pattern in a busy road of a city, right? So how I do it? So more and more traffic patterns I offer, right? More and more traffic patterns are different of the last 2 years, or the last 3 years, or last 5 years, or different hours of the day. More and more data or more and more scenario I give to my machine to build up the model. This model will be pretty accurate when I try to get what is the traffic pattern scenario will be in the next 5 hours or next 10 hours. So it will generate more accurate information because it has learned a large amount of data which was present in the history, and that's the way it has gathered the experience, and that's the way its performance is getting enhanced. So if we look into the tasks where machine learnings are very well used, right? These are some of the tasks, and we know that this is actually there is a predominant focus of machine learning in the game development. Okay, a lot of work, that means, yeah, actually most of our, or maybe all of our computer games are having some sort of machine learning at the back end, right? So that we have a very the very expert computer player gets plays with us, right? And that's the way it also learns it. Okay, it learns the moves of the opponent, it learns the moves of the best players, and tries to develop that. There's a predominant use of machine learning in pattern recognition. It can be handwriting recognition, it can be recognition of the words, it can be conversion of the text to speech. So these are nothing but recognizing patterns and trying to understand the patterns, and those are predominantly based on machine learning. In the domain of sensor data processing, where a lot of sensor data have been taken, and based on the sensors, the decisions have been taken, be it in the surveillance, be it in the autonomous vehicles, where a lot of sensor data comes, and we try to tell that, okay, that if I have autonomous vehicle, the vehicle will try to have a lot of sensors in terms of camera visions, in terms of leaders, which are some range sensors of the obstacles, and we try to maneuver this vehicle in a road with autonomous way. So how it does the job? It does the job because it does some very complex machine learning, executes some complex machine learning tasks, which actually processes the data coming from the sensors and tries to understand what is there in the near environment of the vehicle, and then try to take a decision how the vehicle will move in the particular environment, right? And obviously there are a lot of activities in the domain of the merging or the confluence of machine learning and security, right? A lot of security techniques or security processes are now being developed based on machine learning because it has been understood that there are some patterns or some signatures which, if well understood, we can detect that whether there is some threat or there is some attack scenarios which are coming towards the system, and that's the way the cybersecurity and machine learning is now working in a very great way. Be it if it is fundamental that how to understand the signatures of a spam mail, that what are the tokens, what are the tokens being used to float a spam mail, and whether we can understand the tokens and we can just try to delete that. Similarly, there are ways to understand that what are the ways an attacker tries to generate some some malicious operations in my server, some flooding in my server, whether this can be, if this can be understood well ahead based on some machine learning technique, then very easily the threats can be mitigated. So these are only a few scenarios which I have just told you to try to understand what are the very well use cases of machine learning. But there are a lot of other use cases which I didn't mention, like in computer vision, in biomedical applications, in environmental monitoring, in climate predictions, and lot many more. Okay, so so there is virtually that means we have a plethora of applications where the machine learning it can play a very important role. Now let us look into, as I already told, that just to again come to a very fundamental understanding that what is a traditional programming and how the machine learning differs from the traditional programming. So the way it differs is that it has a learning process, right? And how it learns. It learns, if you see the flow diagram for machine learning, it learns from the historic data, which gives that, okay, this is the scenario and this was your outcome. So it's a historic outcome. So based on the historic bet, okay, it's observing or analyzing the historic data and trying to correlate with the historic outcome. In the process, what the model generates is some sort of rules, right, or some sort of hypothesis, right, and this hypothesis gets well massaged, okay, by repeated use of a large amount of history data and the corresponding outcomes, and this particular hypothesis becomes concentrated as a very well developed model. Provided the well developed model works fine, okay, then the model can accept the data as an input and can try to get a decision. So you see that in the machine learning there is a building phase, or there's a learning phase in the system, which is not there in a traditional programming concept. In a traditional programming concept, it is the programmer who decides what needs to be done and tries to develop the program accordingly, and the machine works. So traditional programming fails when the scenarios are pretty complex, as well as when the scenarios, when we try to have adaptive type of mechanisms in computation outcome, which cannot be done in the traditional programming model, which can be very well understood, because in the case of machine learning model, because machine learning first looks into the data and then tries to build the model. So if we look into the evolution of machine learning, you will see there are a lot of things which are there in the flow. Obviously, we started from traditional programming, and then the traditional machine learning, then came the deep learning, which I will just touch upon in my lecture. And then came the reinforcement learning, which is something that to learn how to learn, right? To take the best strategy of learning is reinforcement learning. So learning is one strategy which is there in the machine learning. In the case of deep learning, the learning is more autonomous instead of manual process of extracting the feature and then pushing it to the classifier. Deep learning learns the features automatically. And in the case of reinforcement learning, it's a further ahead, where it tries to make the learning process, or tries to make the learning process the best learning process, the best learning path it adapts, so that it can better in quality, and it can also work in the domains where the previous decisions are known, right? And then comes the highest level of learning, where the machine contributes, right? Where the machine actually contributes back to the human, or to the environment, instead of only capturing from the environment and taking decision. The machine tries to tell that what needs to be done to the environment, so that it works very well. And those are done with the intelligence systems. What we're trying to do, we are trying to have the swarm intelligence in terms of our drones and a lot of our sensors, and where we try to give a sort of prediction or sort of knowledge which was completely not there in the domain previously. right? Exploration of new knowledge is something which is the next level of machine learning, right? And so let us see some of the interesting ways the machine learning, some good interesting example use cases of machine learning, right? So this is an example of machine learning which tells that a particular okay, that means a particular cost of a particular item, right? A cost of a particular item, this is the cost of a particular maybe a share value, okay, maybe a financial commodity. So a financial commodity, how it varies with time, right? And this is called a prediction problem in the domain of machine learning. Why a prediction problem? Because you see that the values what we can have in this particular outcome is a continuous range of values, which can be maybe from rupees 500 or maybe from rupees 50 to a value of 5,000 or 10,000 or maybe lakhs and crores. So it means that the values what I'm predicting has a large range, and it can be any value within this range. So normally the prediction graphs are continuous graphs because it has all the possible range of values, right? And this is a prediction because a model tries to so if we try to look into the prediction, so what the model will do, in the model we will give the number of days, and the model will try to predict the price of the particular commodity, and that's the way. And obviously we show this actual and predicted because we try to see what is the performance of the model, right? If the performance of the model is very good, then the predicted and the actual will be very close to one another, so we can depend on the model, right? And these type of problems are basically handled with the technique called prediction, or it is also called regression models in the domain of machine learning. This is another type of problems which are handled in the machine learning. These are called recommendation problems. What is a recommendation problem? Recommendation problem is something that if there is the outcome which is X, right? Can we associate other outcomes to this particular outcome X? For example, in a real business problem, suppose you go to a retail web application, right? And a retail web application, you try to choose a product, right? You try to give your choice for a product. Suppose you're given a choice for fruit juice, right? So the retail, suppose Amazon, or suppose Groffer, or suppose Big Basket. These are the predominant retails in the food in the supplying the food commodity. So once you click the fruit juice, okay, you will see several responsive messages are coming, and it's telling that there's a discount in the fruit, there's a discount in the bread, there's a discount in the milk. When you want to, do you want to have it? So how does these recommendations are made? These recommendations are made because studying the behavior of the users who has already purchased fruit juice with fruits, and they have also purchased fruits, and they've also purchased milk, and they've also purchased bread, and so on. So based on the behaviors of understanding the behaviors of the large customers who have already bought the things from this retail, the retail has built a model at the back, which is a recommendation model. It now understands that if provided a particular person buys a fruit juice, the person has a strong requirement of buying fruits. The person has a strong requirement of buying milk, and so on. So it has built a model which is the association model, and this association model is also commonly called as a recommendation model in the business domain, and this is playing a very vital role in the day-to-day business of a lot of retail activities. This is a fascinating problem where when my group at the University of Calcutta works pretty well, and we are doing this work for the last 6+ years in the domain of computer vision. Maybe 8+ years, sorry, not 6, but 8+ years we're doing this work. So So what this work is called the computer-aided diagnostics, computer-aided detection and diagnostics. What we try to do here, we try to employ the machine learning algorithms and try to find out the different types of abnormal informations or different types of outlier informations in the biomedical images, and try to help the doctors to detecting the diseases, and also to classify the disease condition based on the medical data or medical that means capturing the knowledge from the medical data and medical records. We try to build a knowledge model, okay, and this knowledge model guides the doctors to detect and to classify the different types of deformities in the medical images. Last but not the least, as I told, that the security and machine learning is something which are very inherently clubbed up, and this is a good example. What is being done is that you try to find out that what is being happening in the different contexts, and try to explode the signatures in a much better way in the domain of machine learning, which can help in not only in the cybersecurity but many other activities. What we have to understand in a very fundamental way, what machine learning does is machine learning tries to do the perfect guesses, right? And these guesses might not be very exact, okay, but still it helps to a lot of purpose. Suppose I'm trying to buy a particular property, right? So what I try to have, so my plan is to buy it's a three bedroom apartment, right, in a place, say it's a new town, right? If I try to, that means I'm trying to find that what will be the price of a 3-bedroom apartment in Newtown, right? So there are a lot of retail chains which are there, that the property estates, real estate chains which are there, right? And they have this tool. So you give your requirement and you give your location, it will predict a value. Suppose it predicts a value of, say, it's 50 lakhs, right? So now if the property is actually 55 lakhs, it doesn't matter to you, right? Because you know that means your tool or your machine learning model, which has been trained with a lot of this data and and evaluates your result based on those particular models. Okay, it gives a pretty close value which is actual, and with that you can easily go with your budget, right? And similarly, the predictions model for rain, the predictions model for storm, the predictions model for weather is pretty good enough, right? You don't have to tell that, okay, the storm will be around 125.67 kilometers per hour, right? You can tell there will be a storm which a probability of 120 kilometers per hour, right? And that serves the purpose. So that is the crux of machine learning, and how it helps to our solving the problem, or making us very well equipped, right, with lot of application domains, that based on the machine learning techniques which works at the back end of all of those. So the latest contribution, okay, in the domain of machine learning, or the next contribution in the domain of machine learning is actually deep learning. So deep learning is something which is pretty well imitating the activities which are something which are very close to our neural activities, or actually they are trying to imitate the neural activities in our nervous systems, right? And they are efficient. These networks or these deep learning models are based on the neural network models as their backbone, right? And these models are going into the level where they are trying to find a lot of computational functions which are actually done in our brains, okay, trying to emulate those in our computing systems, and trying to develop complex models which can handle very complex types of applications, and can give you very very decisions which are very perfect, right? Which are previously not possible with traditional machine learning. And that's why you see that deep learning. I will touch down deep learning in my lecture, but that's why you will find that the deep learning is so much talked about in the present domain, right? And that is what the deep learning does, right? Deep learning can work on the different levels of your feature extractions. It starts with abstraction of very low level features like edge level features, but gradually, as the network is pretty long, okay, it tries to build the feature space from a simple feature space. It tries to build a very complex feature space and tries to generate a very complex abstractions and very complex classification and prediction outcomes, right? Like it can detect the faces, right, which is a very complex complex object to detect. And very complex tasks like so many objects in a particular environment, so many different types of objects in a particular environment, and still this deep learning model works fantastically to level the objects and to give a complete information of your scene. And that's why the deep learning is so important and so commonly used in a lot of our autonomous applications. So last but not the least, what we try to come out with this type of all these achievements of machine learning is a smarter machine. So a machine which is very close to human intelligence. We are not telling that it will surpass human intelligence, because we all are human. We don't want that machines will surpass our intelligence. But now the scenario has come up where we can build a machine intelligence or based on the machine learning techniques. An intelligent machine which is very close to human intelligence. And that's why there will be the interaction between a human and machine is now possible, because machine is now responsive. The machine has an intelligence. Machine can respond to the real time scenarios pretty close than an actual human can do. So that's why in the smarter world, or in the world which is evolving, which is coming up, is something where you will have the machine learning models or machines will interact very easily with the humans, and there will be joint activity done by the machines and the humans. Obviously, there are some issues like ethical issues, and those issues are obviously there, and those issues will coming up in a more strong way once we have these machines which are very close to the human intelligence, right? And before going to the strategies, I want to just take a couple of questions. If anybody has any question on my lecture up to this. If you have any questions, I can take a couple of questions, or otherwise I will move to my next discussion.
Sir, here is a question.
Yeah.
That is, what is the deep learning inner meaning?
Okay. So yeah. So the word deep learning that means it has two words. That is a deep and learning. So the meaning of deep is that the first of all meaning is that means, very simply you can tell that deep means a deep network, right? And what is a deep network? It is there in my last that means in the last phase of my lecture. What is a deep network? So that is the deep part of it, which means that a network which consists of a lot of hidden layers, a neural network which consists of a lot of hidden layers. The other way of looking into this is that these particular networks can actually extract very deep features. So the features are something which may be very simple features, which are very obvious features, but there are some features which are very deep features, right? Suppose you have to distinguish between two persons, right? It is very easy for for us to distinguish that, okay, this was person X and this was person Y, right? And okay, it's very easy to differ, distinguish by us, because we not only see the eyes on the and the nose and the lips features, but we have some sort of perception or some sort of some deep features our senses can it can carry over. Like deep features means the texture of the skin. The deep features means whether there is a mark in anywhere in the face, the curl of the hair, the whether the person has specs or not. So these are some of the features which are a little bit deep features in a particular image, right? And that helps us to understand. So similarly, the computation model or the feature extraction model in the deep networks tries to work with this type of very hidden or deep features, right? And that's why its name is also called a deep network. That's the other way of identifying a deep network. Okay. So any other questions?
Yes, sir. There is another question. How much ML handles the trade-off between computational time and accuracy measures of the algorithm in medical imaging?
Okay. So you have to. That means if you are talking about supervised network, right? Computation time is not of not that means we need to not to worry about that because models are built offline, right? Uh, so so the most of the computation time is taken in the training phase of your model. So but that is done offline. So you take the model, in that case you take a large amount of data, you train your model, you iterate your model with a lot of different size of batches, uh, different epoch counts, and try to develop the model, right? There are some optimization techniques also, like you can use some dropouts okay, and those are some of the things. And then what we try to come out is a very optimized model, right? And this optimized model can work pretty fast, right? Because it has now been converted to a runtime model which is pretty efficient, right? So the most of the time which has been taken in the deep learning and machine learning is basically the training part of the time, which is most probably done offline. Okay, I can take one more question and then I will again go to the next part, and then I will answer all other questions. Okay, so any one question I can take.
Okay, sir. There is a question. Speech recognition is the application of NLP.
See, the most common application of NLP is called the natural language, right? And a natural language has a different sort of tokens, okay, which are so tokens are nothing but your components of your information, right? That is how you are generating the information is called the token. So what we try to do in the case of natural language processing is basically the text processing. But speech processing, in a sense, is also natural language processing, because in the case of speech, right, you that means you have to, that means it has some sort of language library, right? And that's why you have to, that means that if you have to interpret the speech in a proper way, you have to go through the language context of the language and use that context to generate the information out of the speech, right? But only converting a speech to that means detecting some other features of the speech, like finding the pitch, finding the intensity, finding the frequency component. That must not be NLP. Okay, that may be just simply some spectrum analysis or extracting features from spectrum. But if you are trying to convert a speech to text, or trying to find out the textual content of the speech, right, you have to do some sort of natural language processing. Yes. So I think a lot of questions are there. Sorry, but due to limitation of time, I also have to cover my lecture. So let us move on to my lecture, and I will again come back to my questions, all the questions later in the last part of my lecture. Okay.
Okay,
So
okay,
let's
sir.
move on. Um, So now I start discussing with the, oh, sorry. Okay, now let us try to discuss with the strategies what machine learning has. That what is the common strategy? There are a lot many, but I'm trying to brief only the most well spoken strategies, right? So the most well spoken strategies are something supervised learning, which can be of like regression or classification, and classification may be binary, multi-class, multi-level, and unsupervised learning, which can be partitional, which can be hierarchical, uh, 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 reinforcement learning, and semi-supervised learning. I will try to have a very quick overview of all of this. So when we tell a supervised learning, it means that we have a supervisor, right? Supervisor. So supervisor is nothing but a training set here. So a training set is already a well-developed data set, and that data set consists that, okay, these are your this were your input, and this were your corresponding outcome. So you have a large amount of data which speaks about that these were your data inputs, and this was your outcome out of this data, right? And provided you have that particular training data, whether you can build a hypothesis, right? And that hypothesis will try to predict the outcome from the input, okay? And that it tries to build up with the knowledge of the training data set. Once you build that, it's called a hypothesis because it's not experimentally proven component, because it has an error still, right? It has an error. It is not that it is always predicting the exact value. So what it's trying to do, it is trying to provided now we give an x. So now once we build a hypothesis, provided you were given value of x, it will try to generate a value of y, right? And how it is generated, because the model has learned from your training set, which has a large list of your inputs and corresponding y. So learning that, it has generated the hypothesis, and the hypothesis can now predict the y for any unknown x. For example, a very common example is called the housing price problem, right? In the housing price problem, I have listed the data. Okay, my training data consists of a number, that means the area of the house and the corresponding prices, right? I have a large amount of training data set which consists of the value of x as your area, and the value of outcome y as your price. Provided I have this list, I can generate a particular function. Okay, I can create a function which is a regression function or a prediction function, which tries to generate y or the price of the house, provided a square feet is given. Now this function is something which is this particular blue line. That means as I've tried to generate a linear function, which means that, okay, a linear function means that it will be, your y will be, if I consider that your square feet is x, so your y will be something alpha 0 plus alpha 1x, right? So this is a linear function. The alpha 0 is an intercept on the y-axis, and alpha 1 is the slope of this function, right? And this way we can approximate the functions, the relationship between x and y, and we can write that alpha 0 plus alpha 1x. Now this is the actual line you have, right? Now when you give a particular x, right? And that means as you have generated the hypothesis, it will give a particular value x, and the model will give this particular value y, right? And that is the purpose of building this model, because for any unknown x which was not available in the training set, my model can still able to predict, or still able to generate what should be the outcome y, right? And that's the effectiveness of the model. But if we try to tell that how far the model is accurate, right? The model is accurate, there may be a lot of things you need to consider here. So first of all, you see that for the training data set, you have generated a particular line, a linear function between your x and y, but this function itself doesn't maps all the point in the training data set. So there will be there will be some error in the model itself. But provided this error is within a limit, okay, I don't mind. I can go ahead with the model. So what is the limit? The limit is something that you try to. What is the error? You try to take the perpendicular from all the points, okay, which are in your training data set on the particular function line, right? And take the square of that. Right? So the perpendicular difference is something the difference which is actually your error for each of your x which is given in your training data set, right? And if you sum that, if you sum the square of the difference, that is called the square error, and then you take the mean over all the points in the training data set. So it's called a mean square error. So now, provided we take a mean square error, okay, provided we take a mean square error, and if the mean square error is within a threshold, okay, within a threshold, then you can still accept that this function works perfectly, right? And that's what a supervised learning is. In the case of prediction, the supervised learning can also be a classification. So the difference between a prediction classification problem is that in the case of prediction problem, your y values can be of continuous range, right? And it is of large range. Say y can be from any value between 0 to 1,000 in the example case, and it can have any value. It can have a value of 100.56. It can have any value of 200 from 32. So any value it can have. See the points where we have, it can have any value between 0 to 1,000. Vis-a-vis, when it's a classification problem, your outcome can only be of some possible levels, right? And those are called class levels. So classification problem maps your input to a discrete class level. So the outcome is not continuous as it was in the case of prediction, and the outcome is only a fixed number of levels, right? And that's the classification, which means that if I have given a cupcake and apple, either your outcome can give, that means it will label it as a cupcake, or it will label it as an apple. So this outcome will not be like a prediction outcome, which is a continuous range of values, or it can have a large possible values. So classification only has a fixed number of class levels, and to that your input should be mapped and should be classified. Okay, and classification problem as a so we can also take regression problem in the different forms also. It is okay. An example problem where the advertisement cost vis-a-vis the revenue can be modeled. And see, as I told, that this is the way we try to do. We try to actually have a factor with x, which is a alpha x, plus a factor which is a constant factor alpha 0. So the alpha 0 is called a bias, and this alpha 1 is called a weight, right, of your particular, or you can tell these are the model parameters. These are the model parameters, okay? X0, that is okay, alpha 0 and alpha 1 corresponding to the model, and this is the value of x. And this is a sort of square, okay, square error, which you try to evaluate for all your data elements based on your training data, right? And this is the way you try to do. So the way we try to focus or try to identify regression problem is something like this. We try to find out which is dependent variable. So dependent variable here is the revenue or the price of the house, right? Independent variables, I've only given an example as one variable, but it can be many more. Suppose the price of the house not only depends on the square feet. A price of the house depends on the square feet area. It also depends on the number of rooms in the house. Okay, a price of the house doesn't depends only on the square feet area or the number of rooms, but it also depends on the location, right? The price of the house doesn't depends on the area, on the number of rooms, on the location only, but it also depends on the age of the house. So you see that in the real world problem, there may be several variables which will be actually trying to define your outcome in your regression problem, and those are called the features, right? And we have to identify what are the features in your problem domain, and there are pretty good techniques. Okay, I'm not discussing this due to limitation of time. There are pretty good techniques which tries to evaluate or try to churn out the good features in a particular data set, and that is being done by correlation, understanding the correlation between the features, and there are pretty good ways to understand the correlation between the features and try to work out with the features which are mostly uncorrelated. Those features will be useful features which you can push into the model and you can develop your model. right? And the slope and your intercept are called the model parameters. Now, through your training, you have to adjust these particular model parameters and try to bring your model to a very high accuracy, right? And error function is obviously the measure of the accuracy of your model. So these are some of the things you need to understand whenever you are trying to work with any machine learning model. This is, though I have explained this in terms of regression, but this is pretty well applied for any machine learning model. Now we come to the domain of classification, and when we look into this particular domain of classification, we see that classifications can be of varied type. So the most simple classification is that classification will have two classes. Okay, for example, I just pose the problem like this. That is through my image analysis of a city image, I can tell that whether this is a benign lung nodule or this is a malignant lung nodule. So this is a binary class. So any nodule I try to segment out from my image, right? This nodule can be mapped either to a malignant or to a benign, and this is called a binary classification problem because the outcome has only two possible levels, level 0 and level 1. And this is again decided based on the feature values. So what you try to do, if these are the feature values, this is called a feature space, right? X1 is my one feature. Let us take X1 is the size of the nodule, right? And X2 maybe another feature, maybe the contrast of the nodule or the intensity of the nodule. Let us try to take like that. So you have X2 nodule, okay, one feature X2 and one feature X1. Now for a given image, it will have one value corresponding to X1 feature and one value corresponding to X2 feature. So those two feature values which actually form a point in the feature space because your coordinates are X1 and X2. So these points are nothing but your points which are each of your data element. So each data element has two features. So based on that, you have plotted the data element in the feature space. And so these points are nothing but your each data instance. And now when you plot the data instance in the feature space, okay, if it's a classification problem, what do you need to do? You need to generate a separator. Generate a separator which actually tells that all these data elements are in class 1 and all these data elements are in class 0. If you can able to do that, you have done the classification problem and your problem is solved. But as I tell that this is a very simple example. That means you need to do transformations in the feature space because separation on the feature space might not be so easy. So you may need to do a transformation of the feature space, and then you have to generate the feature space which is sufficient to generate a decision boundary. So the partition between these two classes of data is called a decision boundary, which is being shown here, which is being shown in this particular diagram. So a binary classification problem can be a very simple classification problem, but we can also have multi-classification problem. For example, a good example may be text analytics or natural language processing. Right? And text analytics, by analyzing the text, what I can do, I can categorize, I can classify that news articles either into food or into sports or into politics. If I do that, then what I'm trying to do, I'm trying to generate a multi-class classifications where each of the class has a decision boundaries, and provided the data element falls in each of these class regions, I can label those data elements into the respective classes. So I can label a particular news article either as a food or as a sports or as a politics. That means another way or in use case is very interesting, which is called a multi-level classification. So for the students, you have to be very careful about the difference between multi-class and multi-level classification. So multi-class classification means that with the levels, that means we have more than 2 levels for that means in the class outcome. So class outcome can be 3, class outcome can be 4, class outcome can be 5. These are called multi-class classification. Like the outcome can be food, outcome can be sports, outcome can be politics. But in the case of multi-level classification is that each object or each instance is associated with more than one level, and that's called a multi-level classification. For example, if I tell that this is a movie, right? So a movie has one feature which is a censor certificate. So based on the censor certificate, because a movie cannot have more than one type of censor certificate. A movie can be either of censor certificate X or censor certificate Y or censor certificate Z or censor certificate something like that. Okay. So the censor certificate class of a movie is a multi class classification, because there can be 5 categories of certificates and your movie will be mapping to any one category. But the genre of the movie can be a multi-level. Your genre may be your comedy and romance both. So you see that when you try to see that in which particular genre class the movie is, this can be a multi-level classification because your genre can be combination of both the classes. So this is the difference between a combination of both the levels. So this is the difference between a multi-level classification and a multi-class classification problem. So now let's look into the process or the technique of unsupervised learning. So the unsupervised learning, so what we discussed until now, it's called supervised learning, where we have the training data set, and based on the training data set, we can actually generate the model, and then we can evaluate the error of the model, and we can either go for classification or regression. But in the case of unsupervised learning, there is no prior information about the levels of your data. So that the levels of your data are not there. Levels means that provided we know these are the input of your data, and if you know the outcome of the data, then you tell that you have the level, but you don't have the level, which means that you have a set of images, but nobody has told that whether this image is a cancerous image or it's a benign image. So there was no level for these images. Okay, so you cannot use this data. You cannot use this data to create your classifier, because you don't know that whether this image contains some benign information or whether this image contains a malignant information. And this type of data sets are called, this type of approach is called unsupervised learning. So what you can do, you can still try to find out that whether, that means you take two images, that means randomly from a data set, and try to find that whether these two images is a more similarity or a more dissimilarity. So there will be some features based on which you try to measure the similarity or dissimilarity. Suppose you try to measure the contrast. So whether the contrast of this image is same or the region of an image. Better is to work with the region of an image. Suppose you have two regions of two images, and then you try to find that whether this region of an image and this region of image is very close to the contrast. Whether this region of an image and this region of an image is very close in terms of shape or in terms of texture. So there will be some features. It will also develop a feature space, but instead of trying to generate a class boundary, what you try to do, you try to find out the differences in the feature space. If the differences between the two data elements in the feature space increases above a threshold, then I tell that, okay, this particular data belongs to one cluster, and this particular data belongs to another cluster. And this way we can have more than 1, 2, or 3 clusters in our outcome. So this technique, which clustering technique, is essentially based on the differences in the feature data, okay, between the group of objects, and try to find that whether the group of objects can be close to one another and can form a cluster, or they are far apart from one another, whether they are the part of the two different clusters. And that technique is called clustering technique, right? And this is a common scenario what is a clustering technique is, right? And we try to group the data elements into clusters, and provided we find the good clusters, then our job is done. So what is a good cluster? A good cluster means that if you are telling that this is a cluster, then the difference between the elements of the same cluster should be very small. So the elements which are the part of the same cluster will be very similar to one another. Vis-a-vis the elements which are the part of two different clusters will be very different. And that's the fundamental of generating good clusters. Again, like classifications, it's not always possible to just to cluster the data on the same information space. You might need to do a transformation in the information space to find out to transform the data into a different space where clustering can be an easier way to do, right? I'm not getting in details into this problem, into this, but these are something called the feature space transformations, which if you have to work extensively in this domain of classification and clustering, you have to do it often. Now, one way of doing clustering is something like you just try to partition it, okay? That you have a large number of elements and you try to compare the elements with one another and try to find, okay, hey, this element and this element are far apart. So this you put in cluster 1, this you put in cluster 2. So this way you try to separate out the elements which are there initially. The other way of clustering is that whether we can connect the clusters in a hierarchical form, right? For example, I will give a very simple example. So for example, if you're trying to work with population data, right? So when you try to find out the clusters, okay, in a particular city, you can tell that, okay, this is the population which is in the Dhakuria of Kolkata. This population is maps with the Dhakuria. This is a Dhakuria cluster. Okay, this is a Salt Lake cluster. Okay, this is a Beleghata cluster. This is a maybe this is a Bhawanipur cluster. So these are the peoples who are in different clusters of the particular city. But when you go to the state level, right? In the state level, Kolkata becomes one cluster, and your Bardhaman becomes another cluster. So now within the Kolkata clusters, you have the sub clusters which are Bhawanipur, which are Salt Lake, which are Beleghata, which are Dhakuria, right? So you see that that means it depends on the perspective of how you are analyzing the data. So hierarchical clustering helps when you try to, that means you try to understand the data at a particular perspective. Okay, that means it can be higher up in the hierarchy, it can be lower down in the hierarchy. So based on that, if you try to analyze the data, it can actually also work as a hierarchical clustering. And applications of clustering are many, right? And the application clustering, the most predominant applications of clustering are called the market segmentation, right? In the market segmentation, I will give you a very simple example. Okay, so obviously due to this pandemic scenario, we don't have the Durga Puja shopping started very that it didn't start at all, but try to take a scenario maybe previous years, right? When this month of August is one of the peak season of the people who are shopping for the puja. And obviously during this period of time, we used to get a lot of messages from Pantaloon, from retail stores, from Pantaloon, from different types of garment or retail that hey, this year that may, okay, so you have an offer. If you buy over 1,000, you will get this, right? So maybe the offer which is coming to me is not getting to you, right? Why not? That means, okay, so you are getting a different offer. Why you're getting a different offer? Because you come in a different segment of the market, and I come in a different segment of the market. Now, how does retailer know this? How does retailer know this? That okay, I come with a different type of market. I am a member of a different type of market, and you are a member of a different type of market. Maybe based on my yearly income, okay, I can maximally buy to a store maybe 30,000. Maybe you, based on a different income, you can go and buy from a store at a shot. You can buy above 50,000, and then maybe others, based on their income, they can only buy around 5,000. Okay, so my coupons and my discounts will be like that. Okay, if you buy over 10,000, you will get this discount. Okay, that means when another person goes, they will get a message, or another person will get a message that if you buy over it's a 15,000, 20,000, 25,000, you will get this discount. Okay, fine. And somebody other gets, if you buy over 1,000, you will get this discount. So you see that they have that means the market segment is when analyzed by this particular by this particular retails, a lot of that both in physical stores and both in online stores. Now how they capture this information. Okay, I'm not asking to the participants how this store agents, either physical store agents or virtual store agents, captures this information. Do you have any answer, anybody from the participants? How they capture this information? I will just wait for 1 minute. If anybody has any answer? Do you have any answer? Hello. So can you give me the answer that how these are being?
Sir, one answer I have given, that is Prosenjit Modi has given that through web services.
Yeah. So what they do beautifully. That means I will give the answer when you go to the physical store. Though we are not going to the physical store now, but if you go to the physical store, you will see that there will be persons who will be telling you that sir or madam, please take our card. This is a card which you give a 5% discount on every purchase, right? And we feel that this particular 5% is being offered, okay, is being offered just like that, okay, and we feel that we have got a good deal, right? All of us feel that we have got a good deal because due to this particular card, I got a 5% discount in every purchase. But what they're doing with this is that they're actually that means putting us in their job. How? Because if you have to take a 5% discount, you have to go to you have to take the card and you have to go to the particular billing counter. At billing counter, will scan your card and will put the values of the items you are buying and the total value you are buying, right? And every time you come, whether twice a month or whether once in a month or maybe once in a quarterly, okay, they are recording your data. So what they're doing, they are actually recording your data to generate and to use the data so that they can classify you. So if they can classify you, okay, and when you have done and when you have put the card, it has been asked that you should put your profession. You should, sometimes they also go to further tell your annual salary, but we don't give something like that. But if somebody can give that also, and they can also ask whether you have a car, whether you have a house, or something like that. So what they're doing, they're actually they're instead of that means they work on our data, because it's very difficult for retail to find out that who has purchased what and what is the income category, what is the professional category, what is the social category of an individual. Instead they are giving us the card, and by that we are populating their database, right? And with that database, they can very well do the market analysis. They can find out the category in which market I belong, and accordingly he or she can, that means the retailer can push the information, right? And in the virtual world also, okay, they will ask a registration form. They will ask so many things, details, right? And with that, whenever you are buying, you are logging on with your data, right? And they are trapping that, okay, this particular profile is doing this particular business, this particular purchase. So they are populating the database, right? And this way they are they're categorizing in your market, in the particular value chain, right? I hope that I have made you understand what I mean to say. So this is a very interesting phenomenon, which is being done by the marketing people, and okay, it's called a market segmentation. And similarly, the same thing is done in the case of social network analysis also. In the case of social network analysis, you will get a lot of requests, lot of recommendations that, okay, you can connect to him or her, because so how the networking site know this. Networking site know this because they are trying to find the behaviors. Okay, they are trying to find whether the behaviors of you is close to someone or is very different to someone, right? And based on that, it is associating you to an individual, or slowly you get connected with a group. And this is the way how social network analysis is done. And these all are done with unlabeled data. And that's why it is basically called unsupervised, because nobody has gave a training data that say it's a Omlan Chakraborty has this thing. That means, so you start working with him. It's not like that, right? You collect my data and you try to find out that whether I am close to X type of category or I am close to Y type of category, right? And their way you assign me to X category or Y category. That's so interesting point. And next there's a pretty fundamental stuff which is done in the domain of unsupervised learning, is called noise filtering. Noise is something which you cannot do in the supervised way, right? It's very difficult to do in supervised way. But what you can find out, you can always find out that a particular difference of a noise signal and the difference of an original signal in the particular domain. And if you can know that, okay, this is the say in the case of signal, there's something called power spectrum. So a power spectrum of a noise signal and a power spectrum of your signal, if you can differentiate, right? If you can differentiate, you can easily actually try to get what is then you try to associate what is noise, okay, and what is your clean data, and then you can separate out the noise from your signal, and you can churn out with a very good clear signal, right? And that's the way which is done in many of the real-time noise cancellation techniques which are employed in our system. And similarly for astronomical data analysis, you have a large astronomical data analysis. It is so many things are happening in your space, and you have a lot of informations in terms of a lot of type of okay, say antennas and system uh, telescopic informations which are available from the space, and these informations are similarities, and these similarities of these informations are found out, and accordingly informations in the space are being generated, right? And so a lot of real-time scenarios can be well mapped in the domain of unsupervised learning. Now I want to tell a bit about something which is called a reinforcement learning, and this reinforcement learning is something which was initiated by the concept of the game, okay, of developing a very intelligent game engine. Now you can ask me, that sir, that means you have supervised and unsupervised learning, still why you require reinforcement learning? Because these are the two most obvious cases. Either you have a training data set by which you can learn, or you don't have any training data set, you just try to learn, you just try to go through an exploratory analysis of the data and try to find out whether the data is different or not. And now why reinforcement learning comes up? Now reinforcement learning comes up in a way that, suppose you think of a game, right? So how you develop, just a second, just a second. sorry, there was an important call. Okay, so let's move on. So, okay, yeah. So reinforcement learning is something. Let us think of a scenario which is a game scenario, right? So a game scenario. What happens in the game scenario? Say I try to make a very best game, right? That means a very best game agent. That means a particular game. That means which is very good. That means the agent. The agent is very good. Now, the best I can do is to learn the strategies from the best player in the circuit. So I take the best player in the circuit and I learn the strategies using a supervised learning, and then I can tell that, okay, hey, my game agent is the best. But actually it is not, because based on your supervised learning, your game agent can maximally perform as per the best player. Now, how your agent can perform better than the best? So that is the restriction of a supervised learning. So supervised learning can give you decision based on the decisions which are already happened. Now, if you have a question that, okay, this might not be the best decision, right? I can find out a better decision or a better result out of this. The way you work out is called reinforcement learning. The way reinforcement learning works out is something called a benefit. So an agent tries to work on the solution path. If it actually gets a good solution to this action, it gets a reward, and it tries to follow that path only. If it doesn't, it gets a penalty, and it proves that path. So provided you can have possible X strategies, out of X strategies, you will slowly prune out the strategies which are not giving you good result, and slowly you will converge to your strategies which are giving you better and best results. And ultimately, with given some amount of time, if you try to converge this, you will obviously come to a strategy which is the very best, or which is very close to the very best. So that's the way how reinforcement learning works. And this though started from game theory, but it is now employed in many of the scenarios where we don't have the knowledge in that way, or the knowledge is not very dependable. So there is a thought process that whether we can create a better outcome, okay, than what is already existing in my data. Okay. And last but not the least, there is something called semi-supervised learning, which is a very critical learning, which is not very often used. But as I'm trying to go through the entire gamut, I want to give you the full view of the entire story. So the semi-supervised learning here is a particular way we can try to understand the problem like this. That suppose we have a database of large image, okay, so many images of so many objects, right? Okay, it can be medical image, it can be natural, it can be normal images. Now, if you have to use this data, what do you need to do? The best way is supervised learning. But to do the supervised learning, what do you need to do? You need to have an expert, okay, who will be labeling each of the images. Say it's a biomedical image, an expert or a doctor will tell that, hey, this is a malignant, this is a benign, this is malignant, this is benign, or this is, or say a COVID case. So this is a COVID, this is a pneumonia, this is a non-COVID. So you see, you need to have a large data which should be labeled, and you can then use it. But many of the cases when the data is on generation, when you don't have much amount of time to do the labeling, or the domain is very new, you don't have much labeled data, cannot we do anything? Cannot we build a classifier? We can build a classifier using a technique called semi-supervised learning. So what we try to do, we try to label a small amount of data, okay, a small amount of data by our domain experts or by the already knowledge existing in the domain. So I start with a small amount of data. And this small amount of data will generate a weak classifier. It is a weak classifier because it does not export the full feature space. It does not export the corners of the features. So it is a very weak classifier. Now, to this weak classifier, I pass an unlabeled data, that whatever unlabeled data is with me. Now, this weak classifier will generate good class values of maybe a small amount of data, because those data is very simple, so they can be easily classified. But it will not generate a good class value for the other data because the classifier is weak. So it's not able to classify most of the data. But the data from the initially unlabeled part, which is being classified pretty well, having a good classification accuracy, can now be brought back to the training data, and can now brought back to our training data, and this training data can now build the classifier once again, the weak classifier. So the process, what it works out is that this data from the unlabeled data, a small fraction gets labeled. This small fraction gets back to the training data, makes the classifier a little bit better than the previous weak classifier. And again, using that, I again label a little bit data. So in a iteration process, I will ultimately churn out to have a good amount of training data, and my classifier from a weak classifier, okay, actually becomes a strong classifier, because we're retraining the classifier in each step after the populating the label data and pushing the data from the unlabeled to labeled data, right? And that's all what is there in the case of the techniques. And so in a nutshell, what we try to do, we try to have a designing of a so the system, the machine learning system, how it actually works, whatever is the technique, this is the way we need to do. So we need to understand the environment or the data, which is also called experience, and we try to generate a particular model learner. We try to initiate the learning process, and this learner process will generate a knowledge which is called the model or hypothesis. This is the knowledge we gather from the data, and then we try to find out that how this knowledge, what is the efficiency of the knowledge, what is the performance of the knowledge, okay, through testing. And if it satisfies that, if I see that the accuracy of the knowledge is good, pretty high, through testing, right, then this particular model works fine. If it doesn't work good in testing, we have to reiterate the model with a more amount of data, and we have to try to think that maybe the learner model needs to be more well developed. And this is a process of iteration, a cycle, and cycle. Ultimately it's closed down with the amount of error which we have. And if the amount of error is lower than the threshold, this is perfect. Okay, it can now work. It can now work on real data. Okay, so I now request the organizer that how much time I have, whether I should stop here or I should continue a bit on the neural network.
No, sir, you can continue.
Okay, so how much time I have? And
so actually the time is 4:15.
Okay, 4:50. So I have maybe I have 20 minutes, and then I can spare 10-15 minutes for the questions. Okay, fine. Okay. I will try to move on to the last part of the lecture, and I will take the question at the end of my lecture, right? So this is the last part of my lecture, where I have, after finishing the fundamentals of the learning strategies, okay, in terms of supervised, unsupervised, reinforcement, and semi-supervised. Now I go to a pretty interesting part of the machine learning, okay, and this is very much required because we are now at the era of deep learning, and deep learning networks are based on the neural network models, which are very fundamental. And if you can understand the neural network model, the deep network models are pretty easy to us. So let's start with the neural network model. I will try to make the things very simple and try to make you understand only the basics, right? So a neural network model, also called a perceptron model from the history. Okay, the history it was perceptron, and then it actually developed to a neural network model, neural network. So perceptron neural network model is something what is like shown in the figure, right? So a single neuron, okay, this is a figure of a single neuron. A single neuron consists of a number of input nodes, which can be numbered as x1, x2, and x3, x4, x5 up to xm, and a special node, okay, which is given value 1. I will come to that, why it is like this, why the special node. And all of the nodes have the individual weights. So the special nodes have individual weight with W0, and all others are corresponding weights like W1, W2, W3, W4, Wm, something like this, okay? And what we do, we try to do a summation. We try to do a product of your input nodes multiplied by your weights. We do a product of input nodes multiplied by the weights, like this, xi, yi. And we do a cumulative summation of this, which is done here. Along with this, we also incorporate this W0. Now, this W0 comes as such because the input is always 1. Actually, this W0 is called a bias. So this bias is a particular parameter of the model which is just required to have a more control on the neural network model. I will tell what control it gives you slowly. So now let us try to understand that what actually happens. So this cumulative function actually takes the input, weights multiplied by the inputs, summation with the bias, and then it is applied, then a particular nonlinear activation function is applied over it. And the outcome of the neuron is ultimately the application of the nonlinear activation function on this particular cumulative sum of the inputs with weights plus the bias. And this activation function we have to know. What is the activation function, how it works. But this is a simple neuron in a perceptron network. In a deep network, this neuron will be stacked over one after another, and we will have large number of neurons which will generate the particular process. So some sound is coming. Can you just control the sound?
Yes, please take care of the sound which is coming.
Wait, ma'am, wait.
Yes, one sound is coming.
Yes, sir.
Okay,
Yes.
that's fine. Okay, fine. Okay, yeah. So before going into the activation layer, let's try to go into a little bit simple understanding. So this particular computation can be well represented by vector also. Right? And this is actually the way we do the computation. So these inputs are represented by the vector which is x, and the weights are represented by the vectors which are w, actually w1 to wm. And the way we try to represent it is something like w0 plus x transpose multiplied with the y vector, w vector. Okay, and that is the computation we need to do in each neuron. Now let us look into what are these activation functions, what they actually do. So the name activation means that means it actually defines whether a neuron gets activated or not. A neuron gets activated when the neuron outcome is high, and a neuron is normally called a deactivated, it is not activated if its outcome is low or maybe close to the 0. Okay, so the outcome y, what this activation function generates, is either a pretty high value, which tells the neuron is activated, or a pretty low value, which means the neuron is not activated. So this particular activation function actually decides or actually does the job to activate a neuron or not. So that's why it's called activation function. And if you see that these particular functions are called switching functions, because you see that the nature of activation function. So if I have value less than 0, the activation function will push them more towards 0, more low values. And if you have a value a little bit higher than 0, it will push to the value 1. So it means that this particular activation function actually tries to squeeze all the values which are less than 0 to 0, and all the values which are higher than 0 to 1, right? So it's actually this can be a simple function like this and this and this, but instead of that we have a little bit slow variation at the y. Instead of 0 and 1, which is a sigmoid function, we can also have -1 to +1. The switching may be between -1 to +1. So the outcome y may be the value with -1 to +1. Actually, it is more values will be +1 or -1. Only a small range of values can be something here. So it is actually the values which are squashed to -1 or to +1, and that function is called hyperbolic tangent, or it's called tan H function, right? And these functions are also called squashing function because it actually squashes the value either to a high value or to a low value. And that's based on that, either the neuron is activated or deactivated. There's a typical function which is called a ReLU, or it's called a rectified linear unit. And this is so important because this function is the activation function which is predominantly used in the deep networks. The difference between there are differences between the ReLU function and the other functions, other active functions like sigmoid and tan H. The function of ReLU is something like that. It's the max between 0 and z. So what does it mean? What does it mean? It means that if the summation or the cumulative summation with weight and input is negative, means z is less than 0, the outcome will be 0 because it is max between 0 and z. Now, if your value is positive, greater than 0, then your outcome will be same method of the value, same method of the input. So you see there are two distinct phases of the ReLU. One is which is completely 0. So the value which are less than 0. So the cumulative sum of your weights of your weight multiplied by input plus bias, if it is less than 0, the neuron will generate an outcome 0. But if it is a positive value, the neuron will generate the same positive value, and that's why in the positive half it's a ramp function. In the less than 0 function, it is just the value 0. Now I will ask a question to the participants again. What are the differences you can find out between a ReLU and the other two functions I have shown? What are the differences you can find out? I can accept one or two answers.
Hello, sir. Am I audible?
Yes.
I think in my opinion, in ReLU, the gradient is always positive, whereas in sigmoid and hyperbolic, the gradient after a certain interval, it becomes almost equal to 0. So if gradient will become equal to 0, then the learning process might become slower. So which can be overcome using ReLU activation.
Yes. So this is a very good answer. So this particular phenomenon is called saturation. So these particular functions have a saturation. So you see that you cannot distinguish between an input which is which may be something maybe 4.4 or 5 or maybe 6 or 7, because for all of these inputs, your outcome is same. And this happens a lot when you actually try to do a back propagation. In the case of back propagation, when you try to adjust the weights by back propagation of your network, okay, the contribution of the weights, okay, to your error needs to be understood, and it can be only understood when you change the weight and the input gets changed, and that input generates a change in the outcome. Now, if changing the weights which changes the input doesn't generate a change in the outcome, then you cannot find out that what is the contribution of the W, whether I will increase or decrease. So that is called the, because the gradient, as perfectly told by the yeah, by the participant here, that means you cannot actually distinguish the slope becomes zero, right? And that's what is, because the slope doesn't exist now. You cannot differentiate. So this is the term called saturation, which happens in this in the most other commonly worked out functions. Whereas in the case of ReLU, the significant contribution, which is above zero, for all those contributions, you will always have a particular slope, right? Always your gradient exists. And that's why you can always differentiate between an input which is 5 and input which is 6 or which is half some, which means that if you decrease or increase the weight in a particular boundary, the effect in its outcome and will be propagated to the error will always be visualized. The problem of vanishing gradient will not arise. Whereas in this case, the problem of vanishing gradient will arise. And that's the way. And also you have to understand, this is also a question I'm just putting from your behalf. One of my students asked me that why ReLU is a nonlinear function. Because it looks like this is a linear here and this is a linear here. So a nonlinear function is a function which changes its gradient, right? Very easily you can see that a sigmoid and a hyperbolic tangent is a nonlinear function, because if you plot the gradient is varying. So it's very simply you can tell it's a nonlinear function. Vis-a-vis, in the case of ReLU also, gradient varies, but gradient varies only once. So the gradient varies, hence it is nonlinear, though it is only once, because the gradient was here, and then the gradient sharply varied. A constant gradient, right? So that's why ReLU is also a nonlinear function, right? Though it is piecewise linear. Now this ReLU can be a little bit worked out, in the sense that when the challenge in the ReLU is that. So I will just so it is clear, it is visible. Hello.
Yes, sir.
Yes, sir. Yes,
Visible.
Yes,
My audio is
yes,
visible.
yes, sir,
Okay,
it's
fine.
visible.
So fine. So I stopped in the ReLU. So now I discussed what is ReLU, and so now this is what is called a leaky ReLU. So leaky ReLU is something that in a ReLU, when we have go below zero, okay, then the problem of vanishing gradient again occurs, right? Because we don't have any slope for the outcomes with a zero. So if we want to also find out that what happens when the outcome is below zero, and we try to find the contribution of the weights in the error function, it is suggested, or it is normally worked out that we go with something called leaky ReLU. So what is a leaky ReLU? Leaky ReLU is something where we don't actually make it zero, but what we make a fraction 0.016, okay, 0.01x. So the scale here and the scale here is different. It is a much narrower scale here, and that's why we have a very smaller variation compared to the actual variation in the positive half. Negative half variation is very that means okay, say around 1/10 or 1/20th times of that here. But still this helps us, because this helps us in the finding the gradient when the outcome is below zero. Still we can find the gradient, so we can export the network in a better way, which we wouldn't have done in the case of a normal ReLU. Now another type of activation function is done, which only gives the probability score, right? Instead of a 0 or a 1 or a switching function, it works with the probability score, and this is that is not used very often, but this is very well used in the case of a classifier at the last stage of a network, when we try to classify, and the classification is basically done on the best of probability. So it takes the input, takes the neuron values, and it tries to maps up to a probability score, right? And that is called a softmax classifier. And this softmax classifier comes at the output, in in the many network applications. So now you can ask me that why you take nonlinear functions, nonlinear activations maps the input to a nonlinear domain, right? So you see that many of the real function, many of the real data elements, okay, cannot be well identified in the linear domain. So instead, we have to do the nonlinear domain, where if you have a nonlinear partition, it can be the data can be well identified. Okay, and that's the way we can understand why what is the significance of this nonlinear activation function. The nonlinear activation function maps the outcome of the neuron to a nonlinear field, and that nonlinear field helps us to generate the class boundaries, nonlinear class boundaries, rather than a linear field. Okay, and then we can go on building this into layers, and that's called a neural network, right? A single perceptron can build up a neural network. In a neural network, standard neural network, what we have an input layer, we have a hidden layer, and we have an output layer. The output layer, that means it's output nodes, and output nodes in the output layer can be more than one. So the way we did for all the inputs and one node, in the case of perceptron, okay, it will just follow the same policy. So all these inputs will be combined with the weights multiplied by their individual, that means the weights for each of these hidden nodes. Each of the hidden nodes will have different weights. So you see that a Zi, so a Zi is one hidden node, and for that you have a weight which is W0i, which is the bias, and we have Wji. So J is the input, and I is the particular node concerned in the hidden layer. So this I will be 1, 2, 3, 4 D1 based on the number of nodes in the hidden layer. And then when we go to the output, this output also may be more than one. So the output may be Yi, and this Yi will be again a weight combination of the hidden nodes plus the bias in this particular layer, and then the activation function comes, and then it generates an outcome Y1 or Y2. So you see that it is just the same idea of a perceptron network, just in a more connected form, and it forms a very basic single neural network. And when we look at a neural network, you have two things I have already shown, that one is the weight, one is the bias, how they helps us, how we do that, right? And the way we do that, we have to adjust the weights and biases. But how we do that? Let's come in the case of weights. The weights, initially we can start off with random weights and we can try to form a network. But then we will use the training data to train the network. And what we can find that the training data, once we push the training data to a network, our initial weights, what we have fit in the network, leads to an error in the outcome, because the outcome should be 0, but it got 0.8, and that's why it's an error. So what do we need to do? We need to adjust the weights, and this adjust the weight is basically done through a process called backpropagation, and through backpropagation we adjust the weights, and ultimately we come to a weight fitment or weight fitting of the network, which gives a very low error. And what is the effect of bias? See, the effect of bias is shifting the switching function left or right. Okay, so how it happens? See, all these plots are of the same switching function, but they're different because the biases are different. So if a bias is something like a minus. So if the bias is negative, okay, then what we have, you have a switching function which switches maybe after -5, whatever the value it switches to up high. If we slightly increase the bias, the positive, we see it switches from 0. If we further increases the bias to positive, it switches from a positive value. So the outcome which actually fires the neuron, okay, the cumulative sum of inputs of the weights multiplied by the inputs and the bias cumulatively, which actually fires the neuron, okay, that particular base value is dependent by the bias. So if the bias is negative, right, the switching can occur prior. If the bias is positive, the switching can occur at a much higher positive value. Okay, so so that's the way it can actually work, and that adjusting the bias actually shifts the particular network. Okay. Yeah. So this is the way how the network is being trained. In the forward path, we have already seen a network can go to the backward by adjusting the parameters, and it actually tries to minimize this error. Okay, so this is the wet, this is the wet, this is the wet where we try to train the wets, and this is the initial wet, and then there is a derivative of the error, the error of the loss we defined by the L, and it is a derivative of the error in respect to a particular, in respect to the wets, and there is a learning parameter called eta, how fast we increase or decrease the wet parameter so that it actually goes to the wets, which give you a very low loss. So in each iteration of the training, weights are adjusted in this way, and the loss is estimated. Once we find that the loss is very, very low, then we stop this iteration and we converge the network there. So this is called the weight update of the network, and it goes on and on of a large training set by iterating over all the training data over multiple times, right? And that's the way how the neural network training is done. Not going into much into details. Now I will just quickly that in the case of neural network, okay, I actually take the data all in a one input node channel. Instead, if you segregate the data, if the data is spatial, right, like case of an image, if you segregate the data and we try to operate on different different combinations of the inputs in different way, that's called the convolution kernel. And this convolution kernel defines a spatial segmentation of the data, and that is actually done in the convolutional neural networks, where instead of taking the whole image as a single input of a neuron net layer, what we try to do, we try to build up the neuron layer in a fragmented way. So this is one neuron built up, one neuron built up, one neuron, that means a neuron built up, and these are done by the convolution layers, which works on the patches of the images, right? And these are the ways the neuron build-up works up, and the kernels moves over the entire image and tries to generate the data for this neuron, right? And that is the way the neural network builds up in the case of convolutional neural network. I will not go into much details due to limitation of time. I'm just closing it. So the normal. So if you just try to step up to convolutional neural network, you have just try to understand that convolutional neural network is nothing but the same weight adjustments, but weight adjustments are done in the spatial distributed domain, and the weights are nothing but a convolution kernels which convolve with a piecewise discrete data, and this discretization is done on the image patches. So the entire image is broken up into patches, and on each patches the convolutional neural network works and tries to evaluate a particular data, a particular value, which is a neuron value, and then and there is also some other things which are done. These neuron values can be again subsampled in the terms of pooling layer, where we try to compress the neuron values into smaller number of neurons that it is originally, and that is called the max pooling, where we try to reduce the space. So you see that a 24 cross 24 neuron space, okay, fine, and N1 channels with a number of filters is reduced to 12 cross 12 neuron channels, a neuron space in the max pooling, and then it goes on in the different staggering form of a convolution kernels and max pooling, and then the network ultimately looks like a flattened neural network at the last, and then we try to use a type of softmax type of classifier at the end to classify. This is a typical example of a handwritten digit recognition, where we can have the classes from 0 to 9, and so we train the network with these patterns, and we try to training of networks means adjusting of the weights in the convolution filters, as well as adjusting of the weights in the particular classifier layer. And then once we train the network, and once we train a large number of data, this network will be pretty efficient of solving the problems. And convolutional neural network is a very standard network which is used for image classification or identifying objects in the image. Many networks which have been developed are nothing but the variant of the convolution networks. So at last I want to tell that what is ML in practice. You have to understand the data, right? You have to know what you are trying to do. You have to understand the data. There may be some data pre-processing stuff which are required. It may be pre-processing in terms of cleaning, in terms of integrating the data in the proper form. It may be normalizing the data, right? Because your features can be different scales, right? You can have a feature which is maybe a rainfall, which is a millimeter, okay, a temperature which is on centigrade, right? It can be a water volume which may be on some cubic liters. So you see different features have different type of scales, and you have to, there is some standard normalization procedures to bring the data to scales, and that is actually the pre-processing part. And then we develop the models, try to analyze the performance, and again try to consolidate the model with some new knowledge, or reiterating the data and try to make your model stronger and stronger in each iteration, right? That means I know that is very difficult to all of you to understand everything of ML in my one lecture, right? It's a full course I normally take in my university, which is a 20 hours lecture for the ML, and 20 hours lecture for the deep learning techniques. But obviously, what I try to offer you, I try to offer you the nutshell, so that you can just actually just have the initial understanding, and now you can get into your course, which is going into your college, or you can get you in standard books, and that means, and you can learn the topic, right? And there are a lot of things which are available in the platforms. A lot of open source platforms are there. I will not recommend any of the proprietary platforms for ML. There are very good open source platform. You can use the Google Colab. You can use the data sets are there in the Kaggle. Data sets are there in the GitHub. Excellent data sets are there, and you have very beautiful libraries like Keras, like TensorFlow, and you can use those libraries, and you can build a very efficient neural network model. But this is for the students, right? Don't actually just take a library and run your data and try to use the models as a black box. That is worst, because if you work with the model with a black box, you cannot improve the model, or you cannot show that, hey, this is my contribution, because whatever is done by the model. It is not your contribution. You are just working as an operator of the model. So don't, being a computer science graduate, don't become an operator of the model. Rather become a model developer, and rather become a model integrator, right? So you have to know the insights of the model. What are the number of what are the functions you are implementing in the model? How you are training the model? That means what variations you can understand, you can impart in the model. How you can minimize the error in the model. So all this has to be understood by means of understanding the model mathematically, functionally, programmingly. Okay, programmatically. So it's not a stateway policy that, hey, there are libraries, you take a model, pass the data, and come up to your supervisor or to your teacher that, okay, I have come up with a very beautiful answer. But then what you have worked out, you didn't worked out as a computer science graduate. The way you have worked out is just a model operator. So don't be a model operator, which are 70 to 80% of the people in data science and machine learning are now becoming only model operators. And this is the term what I use there. Them, but this shouldn't be us, right? So this is a cautious warning, or a cautious input to all of you who are students and who are trying to dive in the path of machine learning. So future of machine learning is a fantastic. I don't have to brief much detail. It is in every space. It is now in cloud. Okay, vastly offered in cloud. It has the power to accommodate a very complex problem. Many domains of problem, large domains of problem, and that's why we are developing courses on machine learning, data science, deep learning for our students, so that they are well prepared to handle this type of problems. So I end up here, and thanks to all, and I am now open to any questions from the audience.
Sir, there are so many questions, sir.
Yeah, please.
Yeah, sir. The first question is whether the neural network and deep learning are similar.
No. Neural network deep learning are not similar in that sense. Neural network is the fundamental of deep learning, right? Neural network is something which actually has certain limitations or certain scope of work. Deep learning mixes the neural network with some of the other techniques, like you have this pooling layer, okay, which compresses the data and also tries to make the information invariant with some of the spatial transformations, right? And that's why it is so important. But neural network doesn't doesn't tries to maintain the spatial correlation, right? Neural network doesn't have the spatial correlation, so neural network takes everything as a flat. So deep neural network, what the ways it first tries to deviate from neural network is that tries to fragment out the data space into some patches, right? And then operate and then try to take the neuron outcomes of those patches, and then try to also go in the hierarchical way to not only to work in one particular analysis, but it goes up into the feature space and builds the feature space in a discrete way. So these are the ways by which it can be done, right?
Okay, sir. So next question is, what is peer grading regression?
What is peer grading regression?
Yes, sir.
Can you just explain a bit what is that? That is in what context he is asking? Peer grading, because this is this may be something from application he has quoted from application context. It is not a very fundamental. That means fundamental regression. Maybe some application. What's the context? What's the context of this question?
That is customer crunching.
Okay. I got it. So customer churning, yeah. Customer churning is something that you try to predict some features of the customer, right? And so that what you have to need, you can use different regression models, but customer models are mostly people tries to work with classification as well as some sort of recommendations. Okay. You can still use regression because regressions have logistic regression also. So logistic regression is a sort of way how you can do classification. So maybe you can use the customer classification based on logistic regression, right? And logistic regression is something like I have already explained the sigmoid function. So the sigmoid function, you can use a logistic regression where the outcome y, instead of a continuous variable, it's a continuous probability. The probability is like a squashing function with a probability of 1 and probability of 0. And that's what is way. It is a regression, but it is a classification because it pushes the y outcome to either to 1 or to 0.
Okay, sir. Next question is, how to understand a problem is under the supervised or unsupervised learning?
Oh, that is a pretty easy. That is a pretty easy. If you
It's
have
very
a
easy,
good
but some
amount of
student,
level data, you can go for supervised. If you have label data by the domain expert, you go for supervised. If not, if there is no label, you have to find the discriminatory features in the data and tries to separate out the data. So the way we try to separate out this, okay, separate out the objects, okay, is the way we try to do say clustering, and this is the unsupervised way.
Okay, sir. Next question is, and that is the last question, I think, how to perform clustering in case of group image and how to measure Euclidean distance between two images.
So when you tell Euclidean distance, it is not done between images. It is done between the feature space. So you see, that means I have already give you the concept of feature space when I did classification. So what do you try to do? What is the feature space, right? So say every one of us know what is a three-dimensional space. What is a three-dimensional space? A three-dimensional space has x, y, and z coordinate. So provided you give me a value of x and y and z, I can always place the point in my three-dimensional space. Similarly, you try to conceive something as a feature space. So feature space are nothing but your coordinate axes are your feature axes, right? And it is again a sort of process by which you know that what should be your good feature space. Your good feature space are the feature axes which are mostly orthogonal. Okay, so which have a correlation 0. So now, provided you have a feature space, now for a particular data, maybe an image, right? You are taking the feature space, maybe a particular segment of an image. You are trying to define a feature space in terms of intensity. You are trying to define a feature space in terms of say, it's a texture value, or in terms of some. So some feature values they associate, and so you map that data element in the feature space. So there will be a point, and similarly you map the data element with which you are comparing, okay, in the feature space with another point, right? And then try to find that whether these 2 points are very close in the feature space. So now it is a Euclidean distance, but it's Euclidean distance in the feature space. So first of all, you have to generate the feature space, then you have to populate the data in the feature space, and then you have to find the Euclidean distance in the feature space, and then you can find whether they belong to the same cluster or different cluster, right? And that's the way you have to do.
Okay, thank you, sir. A very
Thank you.
wonderful session. I would like to call.
Yeah, I can speak on hours on this, but you know that there is limitation of time.
Yes.
And also the present time is very busy for me due to a lot of activities going at the back end. So I have to really get involved soon after this lecture on that. So thanks, but please keep connected with me. I will be very interested to the people who are working on machine learning. We have a fantastic data science lab in our department, School of Information Technology, University of Calcutta. That means you can connect with us to that. We are working on a lot of projects, a lot of problems are there, and I welcome you all to that, to my research.
Thank you,
Thank you.
sir.
Thank you.
Thank you, sir. So this is a very wonderful session, and now I would like to request our convener of this program, Ms. Inaduti Dutt, to present a small token of appreciation, the e-certificate. And Inadi, please, you take the Inaduti Di. Hello.
Yes.
Yeah.
Hello.
Yeah.
Are you able to hear me? Yes. Arijit, thank you for calling me up, and respected guest speaker, Professor Omlan Chakraborty sir, Principal Ma'am, Professor Dr. Shutapa Mukherjee, HODs of other departments, faculty, staff, student members across the states. On behalf of Department of Computer Application, BP Poddar Institute of Management and Technology, we would like to express our sincere gratitude and and acknowledge you with a token of appreciation, Amlan sir, for such an enriching session, so that the students could actually imbibe themselves with the beginning or the beginning topics of the machine learning techniques. Maybe in future you would again give us certain such kind of talks, so that our students of basically MCA could enrich themselves with the basics of ML. Thank you, sir.
Thank you. Thank you all. Thank you. I'm signing off. Okay. Thanks.
Okay,
Okay.
Thanks
thank
to
you,
all
sir.
of
And
you.
sir,
Thank you.
we will send you the e-certificate by your mail
Thank you.
ID.
Thank you. Thank you. No worries. Yeah. Thank you
Okay.
all. Okay. Stay
Thank you,
safe.
Thank
sir.
you, sir.
Stay safe. Stay
Thank
safe.
you.
Thank you,
Bye.
sir.
Yeah.
Okay. Thank you, sir.
Thank you, sir.
And participant, there the feedback link is given to the chat box in the Google Meet as well as the YouTube also. You will just fill up it, and the session code is also given in the Google Meet chat box as well as the YouTube chat box. So I
Okay.
think you will fill up and then leave the
Okay.
meet.
Okay. Thank you, Arijit.
Thank you, sir.
Yes, the chat box is itself there. Over there, you can get the feedback code or the session code. Yes. Thank you all. Thank you for the wonderful session, sir. We would also like to thank our principal ma'am, Professor Dr. Shubha Mukherjee, for always encouraging us in every endeavor. We would also like to thank our former Dean Academics, Professor Dr. B.N. Chatterjee, sir, for guiding us right from the inception of the workshop. We would also like to express our gratitude to our registrar, sir, Dr. Subhashish Pradhan, for always supporting us. Special thanks to all the respective representatives of organizing and technical team who have taken the pain to organize such a wonderful session. A big thank you to student, faculty, staff, and research scholar participants across the different states. Last but not the least, I would like to express my gratitude to the Department of Computer Applications, student, faculty, and staff members for constantly working day and night in shaping the workshop. Thank you. We are signing off.